All right, so welcome everybody. Today we're happy to have Hao Shen from University of Wisconsin-Madison, who will tell us about stochastic quantization, large N, and the mean field limit. Thanks, Hao.
Okay, thank you very much. Thanks for the invitation. So this is this talk based on joint work with Scott Smith, Rong Chan, and Xiangchan Zhu. So I'm going to talk about the following question. So in quantum field theory, there are some models where the field takes value in an n-dimensional space. So the question is, what's the asymptotic behavior of such models when the dimensionality of target space n gets large or tends to infinity? So the perspective I'm going to take to study such large n problems is called stochastic quantization. Okay? So stochastic quantization is a procedure which formulates a quantum field theory in terms of stochastic PDE. Now, as you might know, so in the recent years, there are some lot of progress in the development of theory of SPDE. So in this talk, I'm going to use stochastic PDE method to prove a few results regarding large n problems for, well, in particular for a quantum field theory model called the linear sigma model. So maybe I start by recalling what is a quantum field theory, right? So a quantum field theory model can be thought of as a measure defined on the space of fields, like the phi here, and it takes a form of exponential of a certain action, and the expression here is a particular model called the phi4 model. And the action is given by it has a quadratic part, which is grad phi square and phi square, and if this is the only part, then this is just a Gaussian free field, which is I guess object everyone knows, and then besides the quadratic part, it also has a quartic term, phi to the power 4. That's the name phi4 model. And here the m is like a mass parameter, and the lambda is a coupling constant. And then you just integrate this, and this gives you an action. Integrate over a d-dimensional space or torus. So, well, if the dimension is the underlying space dimension is 2 or higher, then well, so far this expression is completely formal. But if dimension 2 or higher, then this requires a procedure called renormalization to make sense. There are, besides the phi4 model, of course, there are other models in quantum field theory defined by different sort of fields or actions. For instance, the famous Yang-Mills model, where the field is not a real valued function, but is actually a Lie group or Lie algebra valued one form. And the action is also different. There are also many other quantum field theory models. So what is a stochastic quantization, as the word showing in the title? So basically, stochastic quantization looks for a dynamic such that the formal measure here is invariant measure. In this dynamic, there's a drift part, which is given by the gradient of the action. And there's also a noise, which is a space-time wide noise. It's just the mean zero Gaussian field over space and time, whose covariance is given by the Dirac delta. You can formally check if you have any Gibbs measure exponential of action, then the gradient flow, the gradient of action perturbed by y noise is formally leaves the measure invariant, at least formally. Specific to the phi4 model written here, the gradient of this action will give you, right? So the gradient of this give you a Laplacian, and then this give you a linear term, this give you a cubic term. So this dynamic is now a stochastic PDE because it's a Laplacian and it's also a nonlinear equation. So the of course, at the moment, this stochastic PDE is also formal in the sense that you also need a renormalization procedure that which I will discuss later to make sense of it. And also construct a solution to this is called a dynamical phi-4 equation is one of the key examples in the recent development of stochastic theory. So in this model or this equation, the phi here is real valued. What I'm going to discuss today is the n-component generalization of this model. So here, well, the model is called a linear sigma model, but it's just a vector version of the phi-4 model. Here, the field phi is a vector, right? So it has components phi1 to phi n, and it has n components. And in the action, it also has a quadratic part, which is just a sum of the squares. So if this is the only term, then this measure would factorize, and this would be just an independent Gaussian free field. However, these components get coupled in the last term. So this last term is a natural generalization of a phi-4 term, which is just a sum of all the squares of the components then square. So so if you open the square, you would get something like phi I square, phi j square. So the different components actually get coupled here. And it's important that this term has a coefficient which is 1 over n. So you should think of the n as being large. So this 1 over n factor somehow balance the strengths of different terms, right? So these terms somehow they have n terms, and here you somehow have n squared terms. Therefore, it's natural to divide this by n. Okay, so of course, this measure again needs a renormalization to make sense of, which I'll discuss later. We can also write down the stochastic quantization equations for this n-vector model, and this will not be a single stochastic PDE, but it's actually a system of stochastic PDEs. It's a system of n equations, where for the I equation, right? So it's just equal to the gradient of this action in the phi I direction. So the linear term is just the Laplacian of phi I, and then the gradient of this term becomes a sum of phi j square phi I. So this the equations in this system gets coupled via the nonlinearity, right? So the phi I equation depends on the other components from here. And here, so the Cassie I's are now n-independent space-time Y noises. And our question, by the way, so if n equal to 1, then this goes back to the dynamical phi-4 equation, right? So so it's very easy actually. So what we know about the dynamical phi-4 equation is very easy to generalize to this equation or this model for fixed n. However, our question here is the asymptotic behavior as n goes to infinity. So that's the question. So this includes, for instance, what's the asymptotic behavior as n goes to infinity for the dynamic, right? So if there is a limit for this dynamic, that would be a mean field limit type of question. Or you can ask, as n goes to infinity, what's the asymptotic behavior of this field here? Or you can also ask the asymptotic behavior of correlation of certain observables for this field. So I'm going to precisely formulate these theorems that we can prove later. But before I state the precise theorems, maybe I should give you some background about where these questions where these questions come from and why we should be interested. So I'll first show you some physics background. Actually, this so-called large N problems was the very early the very first work was not about quantum field theory. It was actually about the statistical physics. In the 60s, Stanley studied, class of spin models where the spins somehow takes value in a sort of n-dimensional space. And the work realized that if n goes to infinity, then these spin models get much simplified. Actually, it becomes the solvable model, which was called a spherical model. It was defined earlier in the 50s. So as n becomes large, such models can be simplified or solvable. And later in the 70s, in this work, they studied a further question, which is not just sending n to infinity, but they expand certain physical quantities in the parameter 1 over n, and they can do some calculations for the terms in the 1 over n expansion. And then the first work that brings this idea to quantum field theory was by Wilson, and at the same time Gros-Neveu. Wilson studied the vector version of the phi-4 model, which is precisely what I'm going to discuss today. And they also studied a fermionic version of quantum field theory. And in fact, some results I'm going to prove today was already predicted by Wilson in his paper. Okay, and then this idea was soon applied to probably more interesting model, like Yang-Mills model by 't Hooft, where the gauge group, right? So for Yang-Mills model, there's always a so-called gauge group, which is essentially where the field takes value in, and the gauge group is SUN. So you can also ask what happens if the size of this matrix goes to infinity. It's funny that in reality, in the standard model that describes fundamental particles, the Yang-Mills model is just SU3. So n is just equal to 3, which doesn't sound too large. But still, if you expand quantities in 1 over n or 1 over 3, right? It's still maybe you expand to a certain order. It's still sensible expansion. And more interestingly, the Hooft discovered some relation between this sort of 1 over n expansion with a certain version of string theory. Later, Witten also used this idea to study nonlinear sigma model, like the field takes value in a manifold with large dimension, for instance, CPN. So of course, there's a large literature that this is far from being complete. And what's nice in this sort of idea is that when physicists study quantum field theory, they do a perturbation theory, which means expand physical quantities in the coupling constant. But sometimes the coupling constant can be large, right? So expanding in the coupling constant might not be a good idea. So if n is large, maybe expanding with respect to 1 over n is more reasonable. And also, as n becomes large, we see some sort of a simplification in such models. Certain quantities are computable. There's large literature, but a good review would be one by Moshe and Zing-Justin, or there's a chapter in a nice book by Coleman. So mathematically, as far as I know, there's not much rigorous, not as many rigorous results. I only list a few of them. The two papers by Kupiana in the 80s. In one paper, he studied 1/n expansion of certain observables for the vector phi-4 model, which is just the model I discussed today. And he in another paper he also studied large n problems in nonlinear sigma model, which is a kind of a Heisenberg model on the lattice. There's also some work about Yang-Mills in 2D, where they show that the Wilson loop observables convert to a so-called master field as n goes to infinity. However, the Yang-Mills in 2D is a very special model because somehow the action just becomes kind of essentially quadratic if you choose a special gauge. So it's completely unclear how to generalize this. And very recently, Chatterjee and Jafarov studied Yang-Mills model with gauge group SON on the lattice. So this is again on the lattice. And having a lattice here in this sort of problem means we just completely ignore the small scale singularity of these quantum field theories. So what in our approach, in the SPDE approach, we can precisely describe we directly work in continuum, and we can precisely describe the small scale singularities. So we don't need any lattice. Here is so we prove a series of results, and here's the first one. So we consider a two-dimensional torus, and we can prove that we can prove a mean field limit as n goes to infinity for the dynamic. So this is a dynamic where again, this is a system of SPDEs suitably renormalized, and as we show that as n goes to infinity, it converts to a very interesting limit. This limit is again a SPDE, and actually it's a decoupled system if you assume the initial condition is independent, because in the ith component of this psi equation, this limit equation, it does not depend on the other components. And this equation looks almost linear, as if you pretend this is just a constant, this is just a linear equation. However, the coefficient here is actually the variance of the solution itself. Okay, so this is actually a self-consistently defined stochastic PDE. And the evolution of this equation depends on its own law, which is the variance here. Okay? So this is a very novel kind of, and more interestingly, this is also a singular stochastic PDE, which would also require renormalization. Okay. So this is probably the most natural singular self-consistent stochastic PDE that one can think of, but as far as I know, this was not studied before. We show that n goes to infinity under this norm, the phi goes to psi. So I guess some people in the audience work on this field called mean field limit, and of course this result has strong flavor of mean field limit. Maybe I can briefly recall, right? So the classical mean field limit type results, which perhaps goes back to Sneedman in the lecture notes in the 80s, they usually study a system of SODEs, right? So you have n SDEs, right? So little xi takes value in Rn, for example, RRD, and it interacts with the other particles, whatever, xj, via some sort of potential. And in the limit, you get a mean field limiting equation where yi interacts with the density, it's called mu, and the density is the law of yi itself. Okay? So this sort of self-consistent limit equation is very common.
Could I interrupt for just a second? I'd like to know this expectation that you're taking here. What does that mean in the equation for psi?
It's a variance, but the psi is the variance of the psi is infinity, right? Because if in 2 dimensions, the variance blows up.
Yeah, but I want to know, is that with respect to the CIs, or is it with respect to the equilibrium measure, or what do you have? What's the expectation mean here?
With respect to the Xi.
Okay, so it's a time dependent. It's a time dependent.
Time dependent, yes. At this moment, time dependent.
Okay.
Later,
Yeah,
when I
thanks.
apply this to invariant measure, I'm going to put this in the stationarity. But here it's really a dynamical result.
It's time dependent.
Right,
Yeah.
right.
Thank you.
Time dependent. Okay, so of course there's huge literature, the whole realm study of mean field limit, where people study different interactions and so on. This can be particles, Coulomb gases, or eigenvalues, whatever also show up in mean field game theory. And but as far as I know, this is the first result which study mean field limit for singular stochastic PDE systems. Okay.
So how can I ask another question?
Yes.
Just can you remind me, are we looking on a compact domain here, or is this
Compact domain? Yeah.
compact domain? Okay.
Yeah. Right. Torus. We're working to generalize to food space, but.
And may I ask a question again?
Yeah.
Does the column mean weak ordering? Above in the page 6.
Yes.
The columns.
The columns are, so this is the weak renormalization, which I'm going to explain to you in a minute.
Okay.
Okay. Yeah. So for now, I just give you some general idea what kind of theorem we can prove. The second result is about the invariant measure, right? So this is the invariant measure for the system, which is the linear sigma model. We can prove, actually we can do this in both 2 and 3 dimensions. We can prove that as n goes to infinity. Oh, by the way, so this, again, this interaction term also requires the renormalization. But I didn't put the renormalization because it's kind of different in 2 and 3 dimensions. So just write this formally. And we can prove that as n goes to infinity, the field converges to Gaussian free field, whose covariance is given by the massive Laplacian. Green's function with the massive Laplacian. So if you look at this result, right? So you can formally write the Gaussian free field with this covariance in the following form. So apparently it looks like in the limit, this interaction term just disappeared. So this is far from being obvious, right? Because there are n terms here when squared, the n squared terms divided by n. So this looks a huge term. So it's not obvious at all that this does not play any role when we take this limit, right? So, but turns out this is true, and this was also predicted by physics using perturbation theory. Perturbation theory, roughly speaking, well, as physicists do, right? They can calculate correlations by expanding the interaction, the e to this phi4 term into a Taylor series. And then physicists realized that only the first term would be order 1 in some sense as n goes to infinity. So for the other terms, they can calculate correlations using Feynman diagrams, and just analyze different contractions and so on, and see what's the order of them. It turns out that all the other terms are of order 1 over n or even smaller. And this is why they believe that only the first term, which is just the Gaussian free field, should survive in the limit. Okay, in this result, we have to assume the mass parameter to be large or the coupling constant to be small, which for me it looks like a technical condition, right? Because we work on a torus, so maybe there's not a physical reason, but at this moment we don't know how to remove this this condition, or we don't know if this is essential or not. I'm going to tell you why we have this when we discuss the proof.
Well, you're gonna get a transition even in this model if you move lambda large or you make m negative, right?
Oh,
you'll have a phase transition
even
in
on
3
the torus?
dimensions. Well, you'll see a trace of it. You'll see a trace of it.
Oh, I see. That might be okay. Then
you'll see a trace of it.
Then this condition might be essential.
Yeah, I think so.
Okay.
Yeah.
Okay. Yeah. Okay. That's good to know. So more interestingly, you can study certain observables. So this model has an interesting symmetry, which is the so-called ON rotation symmetry. That is, if you rotate the target space Rn, then the measure is invariant because all the terms here are like the sum of the squares, right? The norm. So so this means it would be more interesting to study certain observables which have this sort of symmetry or invariance. For instance, one observable would be just the square norm of this vector, right? So it's just the sum of the phi I squares and then suitably normalized. And by the way, this also needs renormalization to make sense of. But for now, we just think of this as an observable, which is the sum of the phi I squares. And we want to know the correlation, okay? So Gn is a correlation of this observable at 2 points. And of course, for a fixed n, we shouldn't expect any formula for this correlation. But turns out that as n goes to infinity, we have exact formula for this correlation, okay? So here the hat is a Fourier transform, and the C is just the Green's function for the massive Laplacian. And the formula says it's just the Fourier transform of the C square divided by this. Okay, so in some sense, in the limit as n goes to infinity, this model has sort of solvability. You can explicitly write down the correlation. And so at this point, right? So if you remember the last theorem, we said the field phi converges to a Gaussian free field. So so if I write Z, the Gaussian free field, right? So in my talk, Z is always the linear solution or the Gaussian guy. So if Z is the Gaussian free field, you might think if you just replace the phi I by the Gaussian Zi, right? So just consider this observable called O prime, which is just defined via the Z. Then since phi converges to Z in the limit, you might think the correlation of this observable might be the same in the limit as the correlation of this observable, but that's not true, right? That would be a very naive guess, but you cannot switch the limits in that way. So you can actually compute the correlation of this observable. Since Z is Gaussian, you can compute using weak theorem, and turns out it's equal to 2c squared, which is the same as the numerator, but it's different, right? This sort of correlation formula was also predicted by physicists using Feynman diagrams. Okay, So for the rest half of the talk, I'm going to prove these three theorems. But before the proof, I thought for the purpose of this talk, maybe it's a good idea to just quickly review what we actually know in the case n equal to 1, right? So what can we do for the dynamical phi-4 equation? So just quickly review, we're going to focus on the two-dimensional case because 3 dimensions is much harder. If n equal to 1, this is our dynamical phi-4 equation. The idea to solve this equation is the following. If you ignore the nonlinearity, only look at the linear equation, right? So here the z solve the linear equation. Then this linear equation is very well understood. In particular, the solution of z can be written as a heat kernel convolving the space-time Y noise. And this is going to be a Gaussian process. So z is Gaussian. And you can also easily prove that z takes value, z is a singular object, right? Z is a distribution which is an element that is in C, slightly below C0. It just means it's a distribution that is slightly fail to be continuous function. Since we know the linear equation very well, the idea is just to decompose the phi into a z part plus a y part. This decomposition is very important because here the z is singular, however, it's Gaussian. And the y is implicit, however, y is more regular. Okay, so as we're going to see, in the end, y is almost C2. So if you plug this ansatz into the equation, you can write down the equation for y. It has y cube term, yz cross terms, and z cube terms. Now I should answer your question, what's the renormalization, right? So here the dot dot here means you have to define the z square and the z cube in renormalized sense. And this is called weak renormalization. I'm not going to give you all the details of how to construct these guys, but basically the idea is you just want these guys to be centered. Okay, so that's the only thing you need to know for the rest of the talk. So the expectation of the weak square and the weak cube are 0. Turns out that once you center these guys, all the moments of these guys are bounded, and you can even do a Kolmogorov argument to prove that these, Gaussian, Gaussian square, Gaussian cube are also have regularity slightly below 0. Now, once we have this, then the y equation is basically driven by 3 noises, right? The z square, and z cube. And these guys are more regular than the original space-time y noise. So you can just solve the y equation using a standard fixed point argument, just as what we always do for the ODE or PDE. And this fixed point argument give you a local solution, short time solution for y, and the fixed point lives in the C2 space. So y is almost C2. Okay, so this only give us a short time solution for y. In order to glue together the short time solutions and make a long time global solution for this equation, we need some sort of a priori PDE estimates on certain norms of y. Okay, so this was done by Moore and Weber. The idea, so suppose you just do L2 estimate, right? Then you just multiply the 2 sides by y and integrate over space. So the left-hand side it just becomes the time derivative of L2 norm, right? And then this becomes the L2 norm of gradient y with a negative sign. And then this becomes the L4 norm of y. And here this minus sign is crucial because now you have a minus of a phi-4 of a L4 norm of y. which means you can move this term to the left-hand side to make it into a positive term. And then you have the other three terms. So the kind of L2, the identity you get is this. So left-hand side, you have these L2s, and with the plus sign of L4 norm, and then the other three terms, where the bracket here is just a usual L2 bracket on the two-dimensional torus. Now, in order to get a priori estimate of L2 norm Y, all you need to do is to bound the right-hand side by the following. You should bound the right-hand side by a small multiple of L2 norms plus a constant. And this is easy because, for instance, right, so the first term here is essentially y cubed times z. Now, suppose you just imagine these guys are numbers instead of functions, right? So if you have numbers like a, b, elementary inequality tells you this is equal to a to the power p plus b to the power q, a pq conjugate. So if you choose suitable pq, this is like 4/3, then this becomes the quartic term, right? The other power of z, you don't care because z is a Gaussian. You can bound it anyway. So, so this is how you get a quartic term of y here. The reason that you also have gradient is because when you estimate, because these are not numbers, right? So when you estimate this, you should bound this guy by a positive regularity norm of y and a negative regularity norm of z. And then there's something called interpolation technique in PDE, which interpolates the positive norm as derivative and non-derivative. So that's essentially what's going on, and same for the other two terms. What's nice here is now you can move these positive terms. You can absorb these terms into the left-hand side. So you end up with a bound which is the time derivative of L2 of y is bounded by constant. Therefore, we obtain this L2 a priori estimate on y, and we can glue together the local solutions again long-time solution. Okay, so this is for the n equal to 1. You see, in the SPDE approach, we use a decomposition first, right, to separate out the most singular part of the field, and then we use a a priori PDE control to control the size of the field. And the sign here is important because that gives us a strong dissipation. Right? And to generalize this to arbitrary n, we will also start with such kind of decomposition into z and y, and then we'll prove a priori bound, which now the a priori bound must be uniform in n, because eventually we want to send n to infinity. So first of all, if you just fix the n, then what do we know about the n equal to 1 case can be easily generalized to fix n. Okay, so in particular, we can construct a local solution for this system equation for fixed n, and we can also construct a local solution to the limiting SPDE. But maybe for the limiting SPDE, it requires a little bit of understanding, right? So, so this is our limiting SPDE. I didn't write the index I because it doesn't matter now. And we also start with this decomposition. Decompose psi into z and x. Z solves the linear equation. And now I should explain to you what's the renormalized variance here. The renormalized variance is just the variance subtract the variance of the linear equation. And in fact, in 2 dimensions, right? So both this variance and this variance would blow up. But the idea is that by subtracting them, they actually cancel. So this will be finite. And if you just, right, so psi is just z plus x. So this expression can be also written as x squared plus 2zx. Now we substitute this ansatz into the original equation. We can write down the equation for x. So x satisfies this equation, where this z plus x comes from the psi here. Okay. So then we just do a fixed point argument to solve this x equation locally. However, there is a subtlety here. We still have these products in the x equations. And in particular, we have a z here times this z. And z is a distribution, so it looks like we need some other renormalization for this product. However, the point here is expectation of this guy. So we only care about the law here. So you can just replace the z by independent copy of z, right? So without changing this expectation. So if this z and this z are independent, then you can just define their product without any renormalization. Because recall that the weak renormalization just make the centered. And if this z and this z are independent, they are just the expectation is just 0, right? So there's no more renormalization required, and we also have a minus sign with x cubed, which would be a strong dissipation. Okay. So this is just a local solution theory, and we want to also get a global control, which is uniform in n. Because we want to send n to infinity. So let's compare the two systems again, right? So we have a phi system and the limit system psi, and we do this kind of decompositions, and the z satisfy the linear. So I just write the heat operator as L. Now we have a equation for y and the equation for x. Now the y equation, it looks complicated, but the structure is again y cubed term, yz cross terms, and z cubed terms. And this is the x equation in the previous slides. Okay, the idea to prove that, right? So we want to prove as n goes to infinity, this y converges to this x, which implies phi converge to psi. And the idea is simple. You just subtract the two equations and prove that the difference between y and x as n goes to infinity converge to 0. However, these are two nonlinear systems. When you subtract two nonlinear guys, you should not just control the difference, but also control each of them. So the proof goes by 3 steps. We want to get a a priori bound on y, which is uniform in n. Secondly, we want to have a priori bound on x. And finally, we want to have some a priori bound for y minus x. So I just write 3 lemmas for the 3 steps. The uniform in n estimate on the y system. Okay, so first, why we have these sums and so on, right? So that the reason is, if you just follow Murat-Weber, you would just multiply the multiply yi on both sides. So this becomes yi squared, and this becomes, well, you see now in this sum there's only one term, which is yi to the power 4, and that term is divided by n, which means the dissipation will look like very weak, right? So the yi to the power 4 is over n. That's why we should actually look at the aggregate quantities, the sums of these L2 norms divided by n. Okay, so the estimate we get is again of this kind of structure. It's L2 norms here plus, well, this essentially some sort of L4, right? Because it's a square L2 square. We can prove that this is bounded by a constant, and this constant is uniform in N. Okay. The same for the mean field limit equation, but instead of average, we have expectation here. And in fact, we need not only L2 estimate but also LP estimate. But anyway, the point is it's also bounded by a constant. Finally, we take the difference between the two systems, and difference we call the VI. We also derive certain energy estimates for the VI. Now that becomes more and more complicated, but the structure is the same. You have some L2 norms. You can bound L2 norms of this difference V, and these terms somehow play the role of the L4, right? Because it's like y times this is quadratic then square, and also on the right hand side you have more than 10 terms. Now we should not only bound this guy by a constant. We actually want this V to vanish as n goes to infinity, right? So we must have some mechanisms which tells us that these 10 plus terms actually vanish, not just bounded by constant. So some of these terms you can just bound them by quartic or quadratic terms with a small multiple, and then absorb into the left hand side as before. But for the other terms, it's not that case. So here we need a crucial fact, which says if you have mean zero independent random variables which take value in some Hilbert space, then the expectation of the sum square is equal to the expectation of the sum of the norm square. So this is important because the left hand side apparently look like n squared terms. The right hand side look like n terms. So using this fact, we actually gain a factor 1 over n. And these 10 plus terms, if you just try to write them in the centered form, right, mean zero, and then apply this. So that's why we gain 1 over n, and that's why the difference V converges to 0 as n goes to infinity. And people work on mean field theory might be this sort of fact somehow also show up in other mean field theory results. And by the way, here we need a Hilbert space H, right? So that's why in our a priori estimate we have to use L2 norms. In this sort of SPD results, for instance, the Murat-Weber result, you can also do some LP estimate, but we actually need a Hilbert space here to use this fact. And in PDE, sometimes we want to trade integrability with regularity, but here we cannot do that. So it's pretty rigid here. Okay. So that's a proof of the first theorem. The second theorem shows that our measure converges to the Gaussian free field. Of course, so how to prove that, right? So maybe the first question would be, is the Gaussian free field an invariant measure for the limiting SPDE, right? That would be a very natural question. And turns out yes. So if Z is a stationary solution to the linear equation, right, the invariant measure of Z is just a Gaussian free field, then actually Z solves this equation. Because that's how the weak renormalization defined. If psi equal to Z, this renormalized variance is precisely 0. So Gaussian free field is an invariant measure, but somehow we're not sure if this is a unique invariant measure. Okay, because the standard ergodicity result in stochastic PDE may not apply to stochastic PDE which depends on its own law. So instead, what we can do is the following. we directly compare the stationary solution of phi with the stationary solution to the linear equation. So recall that the difference between the phi and the z was called y. Suppose we can show that y decay like, in this Sobolev norm, decay like 1 over n, then just shows that the stationary solution for the whole system converges to the stationary solution to linear system, which shows the invariant measure convert to Gaussian free field. And in this result, we really need to assume m large or lambda small. Okay, so to prove this, we first use symmetry, right? So, so the yi and the yj have the same law. When we take excitation, it's the same as you just average all the components. So we want to show this guy is bounded by 1 over n. What we proved above was, without the excitation, this sort of average L2 norm was bounded by a constant. And now we want to enhance that estimate to prove that this is actually bounded by 1 over n. It must be even smaller. And we have excitation here, right? So now we need to track that proof to see what was bounded by constant, right? So the a priori estimate I gave above was saying that the L2s plus the L4 was bounded by constant. But actually it was, if you look at deeper into the proof, it was bounded by something like this, where we have some expression, now I just called curly R, and some expression called curly D. Basically, if you recall the structure of the right-hand side of the equation, we have a cubic term in Z. Basically, that's where R comes from. And we also have the YZ cross terms. Basically, that's why we have a structure like this. So what we know is that the R is uniform bounded by constant. And if you just do a Cauchy-Schwarz, then L2 is absorbed into L4 here, and the D is also uniform bounded. That's why it is bounded. But now we must show that this guy is bounded by 1 over n, right? So now if you look at the R, it looks like something like this, where basically it depends on the cubic term of Z. This term, okay, if you just look at this, right? So there's a square here. So it looks like it has 3 summations and 3 powers of n, which would mean it's order 1 somehow. But if you take excitation, compute this excitation, right? So the excitation of this square, so duplicate this, so the sum becomes sum over J1, J2. And what's interesting here is, in the case that the 3 indices are all different, then this guy and this guy are independent because the zi's are independent, right? So if these ji and I and J1, J2 and I are all different, then this and this are independent, which shows that excitation is equal to the product of excitations. And recall that weak product just makes it centered. So this is 0. So the only contribution to the sum is that sum of indices are actually the same, which means this should be 1 over n. Okay, so the excitation of this guy is, but for the D term, there's no luck. This is where we start to assume m is large or lambda is small. So what we do here is we still want to make D centered. Okay, so we just subtract the excitation of D on both sides. So I just subtract the excitation of D and put this back to the term to the left-hand side. And then we do a Cauchy-Schwarz. So the L2 square can be absorbed into the L4 on the left-hand side. And then we have this square of the centered guy. Okay, so I didn't tell you what precisely D is. So D has many terms. A typical term in D would look like this. is a certain norm of the z's. Okay, so so basically it's precisely that we center this guy, so you can do what we did for the R, the same argument, to show that this guy actually decay like 1/n. This is why the difference between the measure and the Gaussian free field decay like 1/n. So this shows that the Wiesenstein distance between the measure and the Gaussian free field decay like 1/√n. I think we can also prove this in 3 dimensions, but that's harder. I have maybe I take 2 or 3 minutes to explain how we prove the exact formula for the correlation of observable. So far, we only use PDE estimate, right? So a priori estimate in PDE only tell you some upper bound. But if you want to prove some exact formula, then we also need a little bit of algebra, not just PDE. So we actually use the Dyson-Schringer equation for the measure. Well, Dyson-Schringer is just the integration by part, or it's so-called loop equation in other contexts. It's just a correlation between correlations of different order. So we look at this is the kind of a 2-point correlation for the observable, and the Q here is sort of 4-point correlation and 6-point correlations for the invariant measure. We have using this sort of integration by part of Dyson-Schringer, we can derive such identity, and then we apply our PDE estimates to show that this 4-point correlation, 6-point correlation actually decay as n goes to infinity. Therefore, this error term gets killed, and we're left with this. So that's exactly the formula. And proving this, well, first of all, the Q over n that actually looks like order 1, because you have a sum, so this looks like n terms here and divided by n. So apparently, it doesn't look like something that would vanish. But the proof is the following. So how do we prove that this actually vanish? Again, it's a decomposition. We decomposed phi into z and y. Z is a linear guy. And by a straightforward calculation, if you just replace all the phi by z, this expectation is 0, again, because the weak renormalization. And then we have mixed terms, like some are replaced by z and some are y. And then by Holder inequality, we need to bound some higher moments of y, right? So either higher moments of L2 normal y, or some LP normal y. And these sort of bounds requires a more delicate PDE estimate that I'm going to not going to show you, but basically it's a kind of bootstrap. First, we just take the a priori estimate and the energy estimate, and then we kind of using the dissipation and the L2 norm in an iterative way, and then slowly bring down the powers of n, and eventually get this sort of bounds. So so that's basically the results and the proofs. And there are some future questions. For instance, it'd be nicer to derive a systematic 1 over n expansion for the correlations, not just the limit as n goes to infinity. We're working on that. And for the correlation, right? So we prove that the phi goes to Gaussian free field. So the leading order of this the covariance is just a Green's function, and we can also derive a formula in the next order. Okay, so next order has a formula, and suppose we can do this on the entire space. Maybe we can prove some sort of a normalized dimension for the field phi. Okay, and of course, we're busy working on the dynamical Young-Mills, and suppose we have some a priori bounds on those models. then of course you can ask, can we prove large N results for the other models, or like a mean field limited kind of result for coupled KBZ systems, for instance. I'll stop here. Thank you for your attention.
Thanks, Hao, for a great talk. Are there questions? You can just unmute yourself and ask if you like.
Could you clarify?
Oh, go ahead.
Could you clarify what you mean by entire space again?
Not torus, but entire R2 or R3.
Then for that, I think you need a mass gap. That's what I pointed in the email before.
Maybe that's also related with what Tom said, right? So there's here we already need the mass parameter to be large. We might be able to maybe prove an optimal range of this, but for now our M has to be very large, and it's not clear that this result will hold for any positive M and positive lambda, because for the moment I don't know. And
So for the
sorry.
Keep going.
Yeah, please.
I just had a different question. When you have this expectation that you subtract in the sort of mean field limiting equation, which, I mean, you say like it depends on the law of the solution, but at the end of the day, it's just some deterministic function. How well do you understand that function? Does it satisfy some equation, or?
The difference between the two systems?
Just just this expectation here.
Oh, this expectation, or?
Well, I was talking about just the one you had for the mean field equation, not different, but just for the mean field equation. But I think it's kind of the same as this here. Yeah.
Oh yeah. This is just the mean field equation, right? So
right, yeah.
So what do we have for the expectation? Well, we have a priori bounds on the expectation of the norms, right? That's what we know. What else do you want to know?
I mean, can you say, does it, I mean, does this, because now it's just a deterministic equation. I was just wondering if does it satisfy some equation, or like, can you characterize it in some other way without reference to the original system, or not? Maybe not.
Yeah, yeah.
Because if you do with constant initial data, then it's just a number, right? And then maybe you could say something about how the number.
That's true. Yeah, that's good. Oh, I see. So yeah, we also thought about that. Suppose you start with the, let's say, suppose you start with a spatial stationary situation. For example, start from constant or zero. Then, well, the Y noise is also spatially stationary. Then in that case, right, that the variance will only depend on T. So that really look like oh, by the way, in that case, you can actually solve this variance, right? So that would be essentially a constant, and you can, so this would be a linear equation, and you can explicitly calculate the variance of the solution, and equate that to this coefficient. So you get an equation, you can solve that.
Right. But okay, but that's a very special case, and you can't do that in general. What you're saying?
Yeah. In general, we don't know. Suppose we know the invariant measure is spatially stationary, then probably we can prove the Gaussian free field is a unique invariant measure for this dynamic. But we are not there yet.
So and when you get your result about when you have large mass and you get a free field, is your mass renormalized? The new effective mass renormalized?
It's a bare mass.
You
So-
just so it's already you get
Yeah, so
your normalized mass is just the bare mass.
So when I say the mass parameter should be large, I mean the bare mass parameter should be large.
No, yeah, but my question is, let's suppose that's true, which is part of your assumption, but now you look at the resulting limit as large n, and you say you get a free field, right?
Right.
And my question is does that free field have the same bare mass, or does it have a renormalized mass?
The same.
It's the same.
The same, yes. That's
okay. Yeah.
Be careful what I mean, right? So my quartic term is renormalized. That renormalization
So
is a mass.
Yeah, okay.
Yeah, so it's already the weak renormalized, and then based on that, it's the same.
But usually wick is not enough. Usually you have to do something more to set it back.
In 3D, yeah, yeah. So when we also prove the result in 3D, and in 3D, yeah, you have a more.
Okay. Yeah. So could you do all this on the lattice too? I mean, I guess everything would be much simpler on the lattice.
Yeah, sure.
But then you might be able to do something more about, what happens in large volume, or what happens for large when you have a phase transition, or you're near a phase transition point.
Right. Yeah, it's good. Yeah, maybe we can also try working on the lattice, but.
Or you can add a magnetic field too. That will break you. That'll always give you a broken symmetry. So you won't have any phase transition once you have a magnetic field.
Oh, okay. I see. Yeah, on lattice would be just the system SPDEs.
Yeah.
Right. Yeah, so we don't have to care about all the singular norms and so on.
Yeah, right.
But somehow the purpose of this project is to actually deal with a singular.
Yeah, but there are also infrared problems that you have to deal with too, right?
Yeah.
So that would be another different focus, I guess.
Right. We're trying to put some weights in the full space and see you can prove results on the full space. Yeah.
No, I think these equations. Can you do corrections in 1 upon n too?
Corrections of what?
In 1 upon n. Don't take the limit. Just look at it for large n, and then get effective equations that give you corrections in 1 upon n.
Oh yes. For instance, for the dynamic, I haven't thought about. For the invariant measures.
Yeah, dynamics. Yeah.
That would be extremely interesting question. But I haven't thought about that. Yeah. I even actually didn't have a guess. Right. Yeah. The dynamic should also have corrections.
Yeah.
There more questions? I'll stop the recording.